Yes, thank you. So I'll have to start this talk with a warning. So this talk is going to be mainly classical. I hope you're still going to enjoy it or appreciate it because the topic arose from this community. Some of our results do extend to the quantum setting, but in general the quantum setting is still not very well understood, so there's work for you, for us, to be done here. Throughout the talk, I'm going to use this classical C and this quantum Q to distinguish between things that only hold in the classical settings and between things that extend to the quantum setting. So like in the previous talk, I'm going to talk about two-prover commitments. So these are commitment schemes where the committer, the entity that is responsible for producing and opening the commitment, consists of two agents that by assumption cannot communicate with each other. I like to think of commitment schemes in general as analogs of putting something into a safe so that you don't get to see what's inside the safe until I decide to open the safe. That's called the hiding property. On the other hand, you know I cannot change my mind anymore about what's inside the safe. So that's called the binding property. Now, a canonical example for a two-prover bit commitment scheme is the one by Crypto et al. That you've already seen in the previous talk because it's somewhat important for our result. I'm going to quickly go over that scheme again. So in the commit phase, the verifier sends a random string A to prover P, and the prover P replies by sending X computed as Y plus A times B, where Y is joint randomness only known to the provers, and B is the bit they want to commit to. And in order to open the commitment, the other prover Q announces the joint randomness Y, and the verifier simply checks the obvious. And Max has already argued why this is hiding, also why it is binding against against classical provers, and can also show security against quantum provers who are allowed to have shared entanglement and can produce their measurements, their messages as a result of measuring their shares of the quantum state. But this proof is slightly more involved and not part of this work here. In the title, I also mention relativistic commitment schemes, which sort of is related to the question we just had before, which in spirit, as introduced by Kant, is just a two-prover commitment scheme, but where the the no communication assumption is enforced by relativistic effects. So on the example of that particular scheme, we're removing the explicit assumption on that they cannot communicate, and instead we put the two provers far apart in space, and we time the scheme in such a way that this communication here is outside of the light cone determined by this communication here, so that by relativistic effects we know Y must be independent of A here. Now, an obvious downside of this approach is that the open phase must take place very shortly after the commit phase, because after all, this light is pretty damn fast, right? So this motivates the notion of so-called multi-round schemes, where between the commit and the open phase there is a sustained phase during which the verifier keeps communicating with the two provers, and the scheme is timed in such a way that every round of communication lies outside of the light cone of the previous communication, and we want that both the binding and the hiding property hold throughout this sustained phase. So this sustained phase sort of mimics the time when the message is in the safe, so you don't get to see it, but I haven't opened the safe because I haven't opened the safe yet, but I cannot change my mind anymore. And the goal, of course, is to have a reasonably long sustained phase. So a very nice scheme was recently proposed by Lungi et al. Builds up on the Crypto et al. Scheme and concretely works as follows. So the commit phase, in order to commit the bit, they just do the standard commit phase of the Crypto et al. Scheme, except I label here the variables with a subscript 0. And now recall, the standard opening would just be to reveal the joint randomness Y0. But now we don't want to open the commitment yet. We want to delay the opening phase while keeping the binding property alive. So instead, what we're going to do is, or how the scheme works, there's the next round of communication, which has very much the same shape as the first round of communication, except that the parties use fresh randomness. So the verifier chooses a fresh A, the provers use another fresh piece of shared randomness, and that's sort of the important part, instead of using the bit B to compute the reply, they use the randomness Y0, or sort of the opening information from the previous round. One important distinction is that B is a bit, Y0 is a string, but we can understand bit strings as elements from a finite field, so this multiplication here is still well defined. And then the next round is in similar form with fresh randomness, now using Y1, sort of the opening, sort of the randomness from the previous round here to compute x2 and so on and so forth. And then the actual opening phase is by revealing the final Y that was used sort of in the last round, and then it's not too hard to see that the verifier can, from the end to the beginning, compute all the Y's, Y1, Y0, and then with Y0 can verify the original commitment. Okay, so if there are too many variables floating around for you to digest, don't worry. I'm going to get back to this scheme and describe it on a more intuitive level later in my talk. I mean, it is easy to see that the scheme is hiding because every new message that the verifier receives is masked with new fresh randomness. So obviously, no information is leaked until the opening phase. What is not easy to show is the binding property. Now, Lunge et al., they did a rigorous analysis of that scheme and showed that indeed it is binding where the error parameter is upper bounded by this term here. Now, if you look at this term, you see that it behaves rather badly in terms of m. If m grows, this super quickly converges to 1, which means we have essentially no security. M is the number of rounds. So n, the length of the strings. So this means for reasonable parameters, m can only be, you can only allow a rather small m here. And Lunge et al., they also did a practical implementation of that scheme, but because this limitation, because by this sort of weak behavior of this bound, and therefore they can only deal with a small number of rounds, they can keep a commitment alive for up to 2 milliseconds. Okay, so our result is, our contribution is a new analysis of the same scheme where we show that actually the error grows linearly in m, in the number of rounds. So in that sense behaves much better. And now we didn't do any practical implementation, but if we take the data from their implementation but throw in our improved analysis, now I want to get some suspense here. We can keep the commitment alive for 10 to the 5th years. So actually our result is much more general. We show a general composition theorem, and then the improved analysis of the Lunge et al. Scheme follows as a simple corollary. And on the way, we also get a better understanding of the binding property of commitment schemes in this setting here. And also want to point out that in independent work, Chailloux, Chakraborty, and Lefrier, they obtained the very same bound on the Lunge et al. Scheme, so achieved the very same result as we did. Their approach is tailored to that specific scheme, whereas our approach applies sort of much more generally as one distinction. Okay, now before I go into the technical details, I want to give you some intuition for why we expect the scheme to be secure. And our approach for proving it secure is by making this intuition rigorous. Okay, so note that the first round of communication is just the standard commitment to the bit P using the Crépeau et al. Scheme. Now the next round of communication is syntactically just a commitment to Y0. Now I say syntactically because per se, we don't really know what happens with the cryptoidal scheme in terms of security when we plug in a string here rather than a bit. But for the moment, I ignore this issue. And then the next round of communication is a commitment to Y1, and so on and so forth. So schematically, what goes on is the following. First, the provers put the message into the safe. But then, instead of revealing the code that opens the safe, they put that code into a new safe. And then, instead of revealing the code that opens that safe, they put this code into a new safe. Right? They keep going like this until at some point they reveal the code that opens the last safe, and then the verifier can open one safe after the other up to the first one and retrieve the original message that was placed there. Now the question, of course, we want to know is whether this composition of commitments is still binding. Now what we're showing is the security of twofold composition. So if we look at, say, composing these two commitment schemes, these two safes in that way, we get another secure commitment scheme, and then we can just apply this composition repeatedly. We can apply it to this can then compose this composed scheme with this one to argue that this is now a secure commitment scheme, and we can keep on going like this, and in the end argue security of the Lunge-et-al. Scheme with a linear blow-up in the error parameter. Okay, that sounds easy enough. There are a couple of hurdles that we had to deal with. One is that the standard definition for the binding property turns out to be unfriendly for proving such a composition, so we had to come up with a new definition for the binding property, which we showed to be equivalent to the standard one, but this new one turned out to be handier to work with, at least for our purpose. Now there's going to be another hurdle I'll talk about later when I get there. Okay, now I don't have much time to say too much about the new notion of binding. Let me just say, I mean, the intuition for security of a commitment scheme is that we want that after the commit phase, after I've put the safe on the table, there exists a string S hat, which sort of mimics what's supposed to be inside the safe, so that no matter what the provers, no matter how the provers behave in the opening phase, the string that the verifier will accept in the end is that string S hat, except with small probability, or the verifier rejects. I mean, that's sort of the intuition behind the binding property of commitment scheme. And our new definition is one particular way to make this intuition formal. It's not the strongest possible way to make this formal, but we show that in the case of bit commitments, it's equivalent to the standard notion of binding that is used in the context of two-prover and relativistic commitments. Again, I don't have time to go into the details, but let me point out that the cryptoidal scheme as a bit commitment has been analyzed and proven secure according to the standard notion of binding, and therefore it's also secure according to our new notion of binding because they're equivalent. Also recall that in the end, we also need to understand the security of the cryptoidal scheme as a string commitment scheme. Okay, so let me move on to the composition theorem. So what do we show? We start with two rather general two-prover commitment schemes. There is some restriction, like in the first scheme, only P should be involved in the commit phase and only Q should be involved in the opening phase. And so, and only Q should be involved in the commit phase of the second scheme, but the opening phase may be more general in the second scheme. Now, given two such commitment schemes, I'm going to construct a new one, which I call the composition of the two. In order to commit with respect to this composition, I just apply the commit phase of the first scheme. But now, in order to open that commitment, I do something more involved. Instead of just revealing the opening information, I'll now use the second scheme to commit to that opening information, and then I open that commitment, and the string that the verifier accepts from that opening, he then uses to check the opening of the original scheme. Maybe that sounded complicated, but it's nothing else what I said earlier, that instead of revealing the code that opens the safe, I put the code into a new safe and then open that safe. And what we show is that if the underlying commitment schemes are binding, then so is the composition with the error parameters simply adding up. I wanted to give some intuition about the proof. I see I don't have time for that, but let me say that the intuition behind the proof is rather simple. You just have to apply the security of the underlying building blocks in a clever way, and then we can put things together and get what we want. Making this intuition formal is a bit subtle. One has to be very careful with all the different probability distributions that one gets in the proof, but we can do it. Okay, let me now put things together. So now we have this composition theorem which I want to apply repeatedly to prove the security of the Lungi et al. Scheme. Now one thing, or the only thing that we have to do is we have to show that the Crypto et al. Scheme is also secure as a string commitment scheme. Bummer, turns out it is not secure as a string commitment scheme. It does not satisfy our notion of security. It's not the end of my talk. Cannot go to lunch yet, sorry, because we could fix it as follows. We introduced yet another one, slightly relaxed version of the binding property, which we call fairly binding. We could show that the Crypto et al. Scheme as a string commitment scheme is fairly binding, according to this, our notion. We could also extend the composition theorem to this slightly relaxed notion of the binding property. So then we were in business. We could apply the composition theorem repeatedly and conclude security of the Lungi et al. Scheme as a fairly binding string commitment scheme. And then as a last step, as a last observation, the overall scheme doesn't have to be a string commitment scheme. The overall scheme actually is only a bit commitment scheme. And if we restrict the input of a fairly binding string commitment scheme to 1 bit, the scheme is actually binding according to the standard definition. So that in the end, we do have security of the Lungi et al. Scheme with a linear growth of the error parameter in terms of the number of rounds with respect to the standard security definition. Okay, so wrapping up, we have an improved analysis of the Lungi et al. Scheme with a linear instead of doubly exponential blow-up of the error parameter in terms of the number of rounds, which means that, at least in principle, we can keep a commitment alive for 10 to the 50 years rather than 2 milliseconds. On the way, you obtain a better understanding of the binding property in terms of new definitions and relations among them, and main result is a general composition theorem that one can apply to many different schemes. There are some natural questions that arise from this work. For instance, for the composition, we had to restrict the shape of the schemes slightly. It doesn't seem to a big deal. Most of the schemes you would think of, satisfies or fits into this restriction, but still in general would be interesting to see whether you can get rid of these restrictions. I mentioned that the security definition that we use is equivalent to the standard one that is typically used, but also mentioned that it's not the strongest possible one. So there is room for improvement in extending these results to a stronger notion of the binding property. And also it's interesting to see whether the scheme is secure against quantum attacks or not. And I want to point out here there has been some recent progress on the last 2 points here, but there's still open problems. And, but that's for future work, and for now, I'd like to thank you for your attention.
We have time for a quick question.
In the end, you kind of truncated the whole thing to 1 bit, so you made a bit commitment scheme, which seems a bit wasteful. But it looks to me at the first glance that if you take half of the bits, would that be then a secure string commitment scheme? At least with the, we don't know what the definition should be, but is there any problem with that?
Yeah, I think if you, let me first say, if you don't, if you take it as a string commitment scheme as it is, it still satisfies of the fairly binding property. I mean, it's still, some security left, which is good enough in many applications. Okay, if you just cut out half of the...
Like you say, we require that it has to be
so
all
my
zero
intuition would
half.
say, that would then actually give you a string commitment scheme secure according to the standard definition or to the stronger definition. I would have to double check the details, but sort of intuitively I would expect
Do we have a definition?
Sorry?
Do we have a, for your epsilon, for your,
Yeah, so the new definition is general for string commitments, and in the case of bit commitments, it's equivalent to the standard one. Yeah.
Okay.
And I guess we're out of time, so let's thank Serge and all the other speakers of the session. And it's time for lunch.